I'm Anna Hoffman, and welcome to this episode of Data Exposed Live, especially this episode of Something Old, Something New. And today I have once again with me, Buck Woody. Buck, thanks for joining us today. How's it going?
It's going great, Anna. How are you doing?
I am good. Let's kick off by taking a look at your shirt. What do we have today?
Yes.
My password is the last 8 digits of the last 8.
Correct. Yep. I've calculated it. You know, I don't sleep and I have a lot of caffeine. So one night I just sat up and I just calculated it and I thought I'll just trim off the last 8 characters and I'll just use that.
Wow. Is there a last 8 or isn't that kind of the point?
I don't know. Probably. It was when I was calculating it. So maybe that's
you reached an end and you said these are the last 8.
It's true. It's true.
Awesome. Well, we have a kind of exciting show today.
Yeah.
Today, the episode is called That's Really Deep. Do you want to give any sneak peeks as to why it's called that, Buck?
Well, it's a deep topic. And did you see what I did there?
Yes, I did.
Well, that's a deep topic. Okay. Well, anyway, we're going to be talking about deep learning.
Cool. I think it's going to be a great show. I'm excited to see.
I think so too.
Where it goes, what puns come out of this.
Yes.
Now, wherever you're streaming us from, whether it's Learn TV, Twitch, YouTube, Twitter, the Reactor, anywhere you're streaming from, we are taking a look at the comments. So keep them coming. Let us know if you have questions. We are happy to answer them. Or if you have a comment about Buck's t-shirt or any of the puns Buck is sure to make during the episode, or just questions in general, be sure to ask them. We're looking at them. We can even kind of display them up as you even say things like hello. So hello to you as well. Go mainstream. I think with that, we're kind of ready to get
those
started.
Questions, definitely ping us. And, we were talking about wells just a minute ago. I know you were very interested. And one time I was digging, and I was digging not a well, but I was actually digging for gold. And I really hurt my shoulder. I really did.
Oh, you hurt yourself digging for gold.
I did.
I'm really sorry to hear that.
Yeah, it's okay, though. It was a minor injury. Okay.
And I don't know where you come up with these.
Well, when you become a dad, it's genetic. You get that.
It just happens.
Here's the deal. So far, Anna, we've been at this for several episodes now. We've been doing this for a while, and you can find all those, and I'll show you a link to those in just a moment. But we've been working through the various parts of machine learning. And you remember, basically, these are just applying various algorithms in the data and letting a result come back out given the data that we have. Now, just as a refresher here, we have these various concepts of things like labels, which are the answers. This is like if you went to school, sometimes the teacher would say, do the odd problems, and then you can do the even problems, and the answer to the evens are in the book, in the back of the book. So you can check just the even ones to make sure you've kind of got the concept. So that was a kind of labeled data, if you will. We're giving it the answer. We're saying, this is a cup, this is a cup, this is a cup, this is a cup. And then we give it a picture and say, what do you think about that one? And we know the answer, but the computer doesn't. And it says it's a cup. And we say, that's right. And it goes, oh, okay, I did get it right. Or no, that's not quite right. And we train it that way. And here, you remember the various algorithms we've dealt with, and we've seen a lot of these. One is classification, and this one's really common for us to use. And then regression, which is actually, we use the word regression here, and it's kind of an interesting word to use for this. But a regression is actually a prediction. So when we say we're going to regress something, we're going to predict something is the way that works. And then we haven't done the anomaly, or is it odd, because, obviously I'm here, so whether it's odd or not. And then we also had these algorithms that were unsupervised. So in this case, we don't know the answer. So we don't know what books Anna would like to read. We don't have a list of all her books. But what we can do is we can start building these clusters. And we did this, I think, just last episode. We built some clusters. Remember that? Maybe it was the episode before that. I forget. Where we put things together and put those sorts of groups in whatever arrangement we want. And that's where we get these recommender systems. People who like this book, or people who like this movie, like that movie, and so on. Have you found those to be accurate when you've done that? You know what I'm talking about, right?
Hit or miss, but for me, if I'm on Amazon and I'm, putting stuff in my cart, I'm usually clicking all the recommendations. Would you also like this? People buy these things together and I'm like, okay, I guess I'm going to buy that as well.
And that's where this kind of data comes from. And there's one we haven't talked about yet. Do you have a Roomba? The little vacuum
I do not.
thing?
I
No,
don't.
you don't have one of those.
You have a Roomba?
I do. Oh, of course I do. I've named it. And I put eyes on it because I work at home and I don't have any friends. And so the cat, Tina the cat, and my Roomba are pretty much the only company I have. So I talk with them. So yes, I have a Roomba. And a Roomba is actually a fairly complicated device. And it works through something called reinforcement learning, which is not really labeled and it's not really unlabeled. It creates its own labels. So it wanders over to a wall and it's got a little sensor. When it sees the wall, it records what it did and begins to learn the path it can take not to go to that wall again. So it's a reinforcement learning, and we see this used quite a bit. So let me pop over real quick, Anna, and show you just this something old, something new site here. Oops, this is completely the wrong web page here. Here we go. This is the right page. There's your picture, the new improved logo that you made me do. If you go to aka.ms/SOSN, you'll see all our episodes. And we've even got this episode, and you can see all of the episodes here. There's a link so you can go find all the recordings. By the way, we'll be also talking about a dog today, and we'll go from there a little bit more. But these references we have today are really useful. Everything we're going to show, and then lots of the libraries and packages that you're going to show, and the code samples. And then we've got all the episodes we did from before and all the links. So if you go through all these, there's just an absolute ton of things that you'll find that we've already covered. All right. So this is machine learning, and this is the stuff you and I have been showing everybody. And now what we need to do is we need to dig, I think, a little deeper. You ready to dig a little deeper?
Yeah, let's do it.
Okay. All right. So deep learning is actually a subset of machine learning. It's part of a broader family of machine learning methods based on something called learning data representations, as opposed to something like a specific algorithm like we've been doing that is for a task. If we want to do a cluster, we learned about k-means. And if we want to do k-nearest neighbors and all these other kinds of things that we were looking at for classification and all those sorts of things. This is kind of the other way around. Deep learning, by the way, is not a specific thing. There's not a deep learning. It's an approach to machine learning. And by the way, machine learning is actually an approach to learning science, in science. And we're going to talk about this a little bit more. So as we think about deep learning, the first thing we need to remember is it can be supervised, just like we saw before. It can be semi-supervised, which means we provide some answers and it figures out its own, or it can do unsupervised methods. So it can be used for all the things we saw before, but in a slightly different way. Most of modern deep learning algorithms that we have, or models, I should say, are based on something called an artificial neural network, or ANA. And so we'll look at those, and they're based on something called propositional formulas. Remember prepositions? Those kind of things put together and logic statements and all. These are propositional formulas that we'll be using. Also, we're getting into a little bit of math here, and we're going to have to be a little deeper today, but I promise we'll give you some links to help figure this out. It can use something called latent variables organized in layers. In things that are called generative models. And we'll take a look at those. And we'll talk about deep belief networks and deep Boltzmann machines and all these other kind of things. Now, neural networks go even back before the 1940s. So some of these things are even, well, they're not quite as old as I am, but they're almost as old as I am. They go
Hey,
even
you
further.
did that one. Let the record show. I did not make that joke.
Yeah, it's true. Now we've been able to calculate these formulas that we used to create these things, starting about 1938. I'll show you one of those formulas. I remember that guy; he was a hoot. But then we haven't really been able to train the models. The reason why is it's computationally expensive and it's data expensive. The more data, the better. An interesting trivia here is that for most machine learning models, there is a point of diminishing return for data. At some point, you can have too much data and the model will begin to overfit. We talked about that. And in our next episode, we're going to talk a lot about overfitting. But at any rate, you can get too much data. But with deep learning, kind of the more data, the better. That's kind of what you want. So we weren't able to train them until we had access to these computational methods and a lot more data. Now, what deep learning does is it uses sort of hierarchies of artificial neural networks to carry out the process for the system to learn. The artificial neural networks are a bit built a little bit like a human brain, but that's kind of like saying a toothpick is a lot like all of the forests on planet Earth, right? It's a very crude approximation. So when we hear that, oh, this is like thinking, it's nothing remotely like that. It's just we call them neurons, and they're connected together in something that'll look a little bit like a web. Traditional programs build analysis with the data in a linear way. In the hierarchical functions of deep learning, the systems allow the machines to process in a nonlinear way. We'll actually be able to do things in parallel. And the deep in deep learning refers to the number of layers. But that's just conceptual. We could have been talking about it this direction, and it would have been called wide learning or tall learning, but we just happened to do it like roots of a tree. Now, what happens is, we can do regressions and classifications and all these things by passing the data through the layers. And the first layer in our neural network, which we'll see in a minute, is just the raw data. It's just a block of numbers. And we have all these cool terms we use. And a block of numbers is really just what we now call a tensor, T-E-N-S-O-R. That's actually an algebraic concept or a calculus concept of tensor. And there's tensor math. These are not that. They're just called tensors because they're a block of numbers. Maybe it's a line, maybe it's a cube, maybe it's a spreadsheet looking thing, but it's just a block of numbers. And so basically then we just keep passing this data through each layer. And we're going to show you kind of how that works. And it basically takes things like geographic locations and makes the machine's pattern even better. So I think we need to stop here for a minute and show an example of this. Do you remember when you and I, gosh, how many decades ago has it been? We went to South Africa. You remember that?
Oh yeah, when we could travel. Those were the days.
Wasn't that an amazing trip? We went to Johannesburg, and then we went down to Cape Town. And just a stunning trip. What a fantastic place. And there was that one day we were there over a weekend, you remember, and our guy that worked with us took you, me, and Bob out to like a safari kind of thing. Remember that?
Oh yeah.
Yeah. And then he pulled over and he said, "Look at all the wild dogs. These are the original dogs." And you and I are going, we got our cameras out and we're like, dogs, and I'm taking pictures. Where's the dogs? Where's the dogs? He's like, they're right there. And I'm like, where's the dogs? And then you remember you pointed to the ground and you said, I think they're right there. And that's actually the same picture just blown up. And if you look at the left, then you start seeing, I think it was like 14 dogs we counted or whatever, because they're just perfectly colored to lay in the shade next to the rocks and the grass, and you don't see them. And we've been able to do things in machine learning by classifications, but this is a whole tough problem here. This is a whole new level. It was a fun time. Remember we got to pet the tiger as well. Was it tiger or lion? We petted a lion, right?
Yeah, like a baby one.
Yeah.
Very
and
small.
The guy was like, you got to be real careful because they'll tear you up really bad and stuff. And I'm like,
don't touch their face.
And I'm like, what? What did you just say? All right. Okay. let's go take a look at classifications now. And by classifications this time, I don't mean the classifications algorithms. I mean, let's classify some of these things, because there's not just one kind of deep learning. There's actually a bunch. The first is what we've talked about, and this is just the artificial neural network, and we'll talk about that. And the important concepts here are things like neurons, the connection, and again, they're not really neurons, but the connections between them. And then there's something called a weight, and then there's something called a propagation function, and then there's something called a loss. I'm going to get you to help us with that later. Would you mind showing us some examples of those a little later?
Yeah, definitely. I got some good ones.
Okay, perfect. All right, good, because this gets complicated. And that's kind of the general purpose artificial neural network, and those were the first that came out and so on. There are more. There's something called a generative adversarial network, or a GAN. And what this one will do is take like a bunch of something and make a new something. It simulates things. You've probably seen where they take tons of faces and they make a computer face, and you're supposed to guess which one is the not real, kind of thing. And they're so good at this. But they can do this with diseases. They can do it with pictures. They can do it with music, almost anything with a generative. Very cool use of deep learning. There's also a convolutional neural network, or a CNN, which is not a news network. And this is basically pattern matching. So we see this a lot, like when you're driving by and they charge you a toll by your license plate. They're probably using a CNN to do something like that. And then finally, there's a recurrent neural network. And basically this uses the connections between nodes to form a graph network kind of thing. And these are used primarily for sequential or temporal, things that deal with time, so that you can, like words come after each other. So the meaning of the word before can inform what the meaning of the word should be next. That's how a lot of your phone stuff, when you're doing the dictation and it can kind of guess the sentence, it's not just guessing certain things. It's looking at the sentence before and saying, well, these words usually follow that one. So these are the general kind of ideas. So let's get into, let's go a little deeper on deep. In 1943, two people, a guy named McCulloch and a guy named Pitts, wrote this interesting paper. Let me just pop this up if you don't mind, the paper they wrote. This time I'll go to the right thing. And this is a great paper, and I've got it linked for you there. But it started out with something called a perceptron. Now, they were actually building on some stuff done in 1938, but they came up with this idea. They were actually studying the eye. How did the eye work? And they came up with this mathematical model. Now, this is not for computers, because there weren't computers that as we know it then. This was just kind of a simulation that they were writing up. And they had this idea of inputs coming in, and then these little things called weights that they would apply a number to, so that they could kind of tweak the number coming in. For instance, if you're doing like black and white photos, you might say, okay, if it's a dark blue, I want that to go to black. And if it's a light blue, I want that to go to white. And then you can make a black and white photo, that kind of thing. That's what they were doing. And they had this concept of something called a neurode, which had an output that would come out on the other side. And these were great. This is a very early perceptron. And with this, you could do some very cool things. You could represent all kinds of cool things and functions that you could do. You could do ands and ors, but what you could not do is exclusive ors and exclusive ands. It couldn't do zans and zors and XNORs and so on. So it had some problems that it came up with. So there is math here that we're talking about, and you can actually see some of this math right here. But it gets a little complicated. Now you're going to help us out with the math later. Let me go and show you that math. The next idea we came up with, here's the function, by the way, because you could put these together to start solving some of those problems with the XORs and the limitations. And you get something called a multi-layer perceptron. I just love the word perceptron. It sounds so 1960s. And this guy by a guy named Rosenblatt in 1958 that did this one. And basically, he came up with this other cool idea. Now, he used a hyperbolic tangent, which we don't use as much anymore. We use a sigmoid. We'll talk about that in a bit. But you can see he still had that same idea. But he said, what if you took this thing and you gave the result to the next perceptron, and you stacked a bunch of them together, and they each did like one thing, just like the eye does. You've got rods and cones, and your brain can separate edges from that sort of thing. And you need a way to trip it to say, yeah, go ahead and fire that, or no, don't. And that was called an activation function. So that's this little guy right here that does this. And so here's some math. And now we start seeing these. And because you have this input layer and an output layer that you can look at, these were called the outer layers. And then the number of nodes you had inside could just be determined mathematically, and they were called hidden layers. Okay, so back to this. And so you get an input that looks like this. But let's drill in just a little bit here, just to get to this, because I want to get to this so you can get to your part where you explain how all this works. This is a little better view of a modern artificial neuron. And you can see that the inputs come in, we multiply them or add them, usually multiply by a weight. And those are the things we can tickle. And that's the only thing we can change, in fact. That goes into a function that you can see where it sums all of those up. And that is then sent to something that says, yes, deal with it, or no, this is not important. So I think a long time ago, you showed us something to do with letters and numbers and the recognition of those characters. And you could say, yeah, it's kind of gray, but it's not gray enough. So I'm going to call that one white. And so it wouldn't send it on to the next layer and so on, give us our output. Now, this looks fairly uncomplicated. You might think that looks complicated. It gets a lot worse. I can show you one of these, by the way. I could show you one of these sort of working. There's a full white paper on this, by the way. This explains a little bit more about how the perceptron works into the projection and associations. But down here, we talk a little bit more. I think I've got a thing in here, and this is linked in your deal there, where it starts talking about those activation functions. But let's do this. Let's go down to 10 milliseconds, and let's generate some data here. This is a site on the web that you can see. And I will tell it, hey, perceptron, I want you to look at the data, this data, this data, this data, this data. I want you to consider it and trigger it, and I want to watch you work. So we're going to do that. And I'm basically going to say, start working. So it's starting to consider the data. And what it's trying to do here is to create a classification formula that it will say, I think at this boundary, remember we did this with classification before, but we didn't do it with deep learning. We did it in another way. I want to figure out where that line should be. And you can see here, it did a pretty good job. And it can even do more complicated functions and all this. And I've got this link for you in this section. Okay. Now I said it could get more complicated, and it can. This is how a deep neural network really looks. And this isn't even very complicated.
Right.
But what happens is we take the picture of the lady here and we begin to tear it apart, and we give it numbers, and it's just pixels. And the pixels end up with numbers, and there could be a whole lot of them. We've only got a few here. And those get torn apart, and we pass it through a network. Now, the first numerical function would be, is it an edge? Is it not an edge? That's all it does. That's all it does. So it takes all those and turns it into the first block of pictures. The next layer says, well, can they be combined? And I've got a link for you in the references in the site today that actually goes through this. And it's just stunning to watch it build a face, and you can do that. And then finally, it comes out with an output layer, and it says, okay, here's other faces that look like that one. So really just stunning stuff. All right, well, this is something, well, hold on a second before I go to there. This is a thing that can do a lot, but perceptrons back in the 40s and 50s were way oversold. the new brain and the computers are coming for your job from outer space. And it didn't work. And then they were way undersold and nobody used them in the 70s as much as they should. So it became a cautionary tale for how we need to think about things. Now, when we fast forward to more modern concepts in machine learning, did you see what I said? Fast forward. Did you see that?
Yes.
Forward. Okay. Anyway, they lay not just in one layer of computation, weights and the interconnections, but in lots. In fact, layers and layers and layers of computation, each passing their results to another layer. And eventually, voila, we have deep learning. And it's part of a broader, metric, as we talked about earlier. And so I tell you what, let's do this idea of the tensors and all this kind of stuff. I think it's easier if we actually see it. And I don't think you're going to make us do all the math, are you?
Well,
you say that.
Yeah, we'll take a look at some stuff. We won't do all the math, but
Okay.
yeah, we'll take a look and we'll talk about some ways that, libraries are really making this a lot easier,
Right.
And we talked about libraries before, even doing machine learning, how libraries in different languages are going to allow us to not have to do all the math every single time. Now, I think
Right.
you and I would agree it's important to understand the math, but once you kind of understand what's going on, there's no reason we need to be crunching and reinventing the wheel every time.
Right. Granted.
So, yeah, go ahead.
No, I was going to say, that's absolutely correct. I mean, your teacher in school said you won't always have a calculator with you, and I'm like,
yeah, it's like, well, yeah, I probably will. If I need it, I'm going to use it.
Right.
But fortunately, we're not in grade school anymore. I know for you, that was a very long time ago.
Yeah. Well, we didn't actually have it then, but yeah, sure.
There weren't calculators then.
No, there were Greek scholars that we usually sat by, but yeah.
Okay. So, actually, when we talk about deep learning, these are technically called frameworks. But basically, they're going to be huge friends because you're not going to have to do the math every single time. Now, we will take a look at an example of what I call shallow learning because we're not using a lot of layers. It's more reasonable to kind of consider the math, but It very quickly gets very complicated. Like you were saying, Buck, when even some of your visualizations, it's going to get really complicated. So there's some things you need to keep in mind. There's some things you can leverage. Now, these are just some of the frameworks that are pretty popular today. This is not an exhaustive list, and this is not the end all be all, but in my opinion and in my experience, these are some of the things that I see these frameworks being used for. So for example, TensorFlow is really used for a lot of production type of workloads, whereas I'm seeing PyTorch being used a lot for research. Now, they're both really great. Great, especially for getting started. There's a ton of content out on the internet, whether you go to Google or Microsoft or whoever. They've all got lots of content here to learn in this space. Then we also have CNTK. Now, CNTK was something that Microsoft came up with. This used to actually be Buck and I's old sister team. But the CNTK project was used a lot in research and also used a lot for various different types of deep learning, very specific types that could specifically take advantage of things like GPUs and FGPAs, which is basically hardware that's better for doing these heavily computational workloads. However, CNTK maybe a year or 2 years ago went into maintenance mode, but it's still very useful, and we see it being used in universities as well as with people that are just learning or have already implemented CNTK. So we're supporting it, but it's not, making these big new strides or announcements anymore. Then you might have heard of Cafe or Cafe 2. This is really good for machine vision. So that's where I see people using these sort of things. Now, Buck, in your experience with these frameworks, does this kind of align with what you see, or do you kind of see different things? Do you use one more than the other?
Yeah, I mean, TensorFlow is the big gorilla in town, right? It's the one that everyone sort of learns. PyTorch comes and goes. Like I see it get real popular and then not as much. And I'm with you. I see it used a lot, taught in school. It's kind of interesting. TensorFlow came from Google, and PyTorch was more Facebook and another consortium. So TensorFlow is kind of owned and controlled more by Google, and they do a great job. but some people had a philosophical difference with that, and so they wanted to kind of go a different way. But this is absolutely the way they do it. But I noticed you got a couple of other things up there, Keras and Onyx, and I'm actually seeing those in huge use. So tell us about those.
Yeah, definitely. Now, Keras is something that you can use on top of something like TensorFlow and CMTK, and I actually have an example of that to show y'all, but it's really going to make things really easy. Like you talk about, these frameworks are making things easy. In my experience, Keras is making things even easier, and we'll talk about how you can make these big, complex models with just a few lines of code. And then Onyx is another interesting one because it's basically a few different companies teamed together. I think it was Microsoft and Facebook.
I think so. Yeah.
And they came together and they basically said, okay, we don't want everyone to have to use TensorFlow or to have to use PyTorch all the way through their, your production pipeline or your release structure. So what they came up with is this thing called Onyx, which is more of a, now I can't remember what it stands for. It's like the Open Network. Do you remember what it stands for?
Exchange, Open Neural Network Exchange, something like that.
There you go, Open Neural Network Exchange. And so really it's more of like a translator. So what this is going to allow you to do is take a model that was created with TensorFlow, for example, and then leverage it by something using PyTorch or even SQL. And even things like Azure SQL Database Edge, we actually support Onyx models. So what this means is once you create a model anywhere, as long as you can export it to an Onyx model, which that's kind of the point of the Onyx capabilities, is to help you export to these models like Onyx, then you can leverage it in something like Azure SQL Edge and actually deploy it and leverage that model, even though you didn't train the model using potentially in the database.
Right. We've got links to all these, right? We've got links to all these. We've got some comments, people asking, hey, where do I find that? And so on. So you can absolutely find everything we're talking about today, all of these. We've got it in the SOSN setup. Just go in there. You'll see something to every one of these.
Yeah, all these links. And, I know you probably came into the stream thinking after an hour, I'm going to be an expert and know it all. But there is so much out there that we couldn't possibly go through all of these. But yeah, there's a ton of resources. And that's what I think is really cool about this space is like, yes, it's moving very fast. Yes, there's a lot of math, but there's a lot of resources for you to learn and get your hands on if that's something you're interested in doing.
Right. And there was also a question, I'll answer it while you go to your next topic there about auto ML. Now, we don't have time to cover that today, but this is a thing where you basically throw the problem and the data at something called auto ML, and it will figure out what to do. So it's a whole other show. Maybe we'll do that at some point. But auto ML is a fascinating new area as well.
Yeah, definitely. And if you're interested in seeing how SQL and AutoML work together, I actually did a few episodes of Data Exposed a little while back with Sia, who is the program manager for Azure SQL Edge.
Oh, wow.
And she was actually pumping data out of Azure SQL Edge into, I want to say, Azure SQL Database, where she was then using Azure Machine Learning and AutoML to basically parameterize and optimize your models without having to do a lot of the work that usually goes into that. So you can go to our YouTube page and check that out.
Excellent.
Definitely recommend that.
So we have libraries and we have frameworks. So we're good to go here. So how does this stuff look? What does it look like?
Yeah, let's take a look. We got a lot of different examples. So let's kind of walk through one. And what I was thinking we would do, Buck, is we would walk through an example and we wouldn't use a bunch of the different libraries. We'll just use some standard Python libraries. And then I'll show you how much easier it gets when you can use those libraries.
Okay. All right. That sounds good.
Cool. So we're going to try to walk through some of the things that you talked about, and hopefully that helps folks kind of cement what you've said by seeing it again in a different way. And again, this notebook is up on our GitHub page, so you can run through it yourself. You can see I'm in Azure Data Studio, just connecting to a Python notebook. Again, these are super useful if you haven't seen notebooks before, because we can mix text and code cells, and we can even store the results. So here what we have is just some ideas, some potential code you could use to, for example, get TensorFlow, Keras, or sklearn. Now what you can also do is just check kind of the versions of these various things, and even see if you have access to a GPU. And you'll see this in a few different ways. If you don't have access to a GPU, you're just going to use the CPU on your computer, which is what, of course I'm going to use. I'm not going to have any GPUs available on this machine. I don't know, maybe you have a brick, Buck, that does have some GPUs
I
in it.
do. Actually, I have an NVIDIA card on this monster here. And just for the audience, the difference between a CPU and a GPU is it's optimized for everything the computer does. GPU is a graphics processing unit and normally handles polygons. And so it's just optimized for math, and a lot of deep learning problems, like Anna is showing you, can really leverage that. So if it's there, both PyTorch and TensorFlow, for instance, can use them. It'll go, oh, I'll use that, and it's much faster.
Yeah, exactly. Much, much faster. So yeah, so these is kind of the libraries you might be using. Like I said, for this, I'm just going to use NumPy.
Okay.
So I'm just going to import NumPy, and then I'm going to define two things. Now, Buck did talk about this idea of a sigmoid, and a sigmoid is really just an activation function, which is going to give us a way to understand if we should basically fire this neuron or perceptron or not, or if we should basically turn it on or off, say yes or no. So that's what the sigmoid is going to do. And then later, when we talk about measuring loss or measuring how close we were to the answer, taking the derivative is going to help us minimize loss. Now, I don't know if you remember derivatives or minimization or optimizations, but basically by taking the derivative, we can then, work towards minimizing loss, which is ultimately the goal. You want to be as close to the real answer as possible, which means as little loss as possible. So we're just going to define those functions so we can use them later. You can see they're very simple. Now, the next thing we're going to do is we're going to create a neural network class. Now, Buck kind of talked about how this works, how it's going to have an input layer, an output layer, and a number of hidden layers. Now, the model we're going to create, why I called it shallow, is we're just going to have 2 layers. So really, we'll have our input layer, hidden layer, and the output layer. Now, you can just initialize this, and it's pretty straightforward. What we're doing is we're defining the input, we're defining the Y. So in this case, we're using a supervised learning method. So we do have some answers for our training data. And then we're just initializing the output. So we're just creating basically a tensor with 0 for every single value that will ultimately try to fill with our predictions. And then for the weights, Buck talked about the weights. One way I like to think about the weights is if you remember the equation for a line. Buck, do you remember the equation for a line?
Y equals mx plus b.
Exactly. So really what we're doing here is very similar to what you learned, way long ago in middle school, whenever they teach the slope of a line or the equation of a line. We're going to be using these weights as our m value. So this is going to help us identify the slope of the line at a given point in, a much bigger picture of sums. Now, what we're doing here is we're just creating some random weights to start with. And like I said, since we have our input layer, our hidden layer, and our output layer, that kind of works out to a 2-layer model. And that's why we need 2 weights in this situation. So now what we're going to do, and again, you'll have all this notebook so you can click into all these great links that we put together. But the first thing we're going to do is we're going to try to add some functionality. We basically just initialized our neural network. We want to start adding this feed forward. So this feed forward process, well, you can see, and again, we've got the initialization. This is the same code from before. We're going to do the feed forward. So here's where we're going to use that mx plus b like we talked about. However, in this case, we're actually, just for simplicity, we're going to assume that the b is equal to 0. And like I mentioned, this is a 2-layer network. We'll have layer 1, and we'll also have the output layer. Now, what we're doing in this is we're using the dot product. So this is NP dot. And this basically just allows us to multiply different matrices or tensors together. So here we're multiplying if you think about it, the line, we're multiplying the x and the m. So we're basically doing the dot product to multiply mx, and we're assuming bias or b is 0. And then on top of that, so that's what we do right here. On top of that, what we're doing is we're going to take the sigmoid. So this sigmoid is, again, just going to tell us, should we fire this or not? Should it be yes or no? It's basically going to make it very obvious between 0 and 1. And then we're going to do the same thing, but our next input for the output is going to be the outputs for layer 1. Right. And we're going to use our new weights for weight 2. And now we have our feed forward defined as part of our neural network. So hopefully pretty straightforward. We're following along okay. So going to go ahead and run that. So now we have our neural network class. Now, the other part that Buck talked about was not just the feed forward, but we're also going to have to figure out, okay, well, how do we perform as we go forward? How do we perform? So what's our loss? And how can we minimize loss? And then we're going to go back the other way to try to update those weights so that we can get closer to a better solution.
So
Now,
this is kind of interesting when we think about this. You remember our do you have questions? And I always put a GIF up in the corner, or GIF. I don't know how you say it, but it's GIF for me. And that's got the teacher that's writing, "I am professor," and he keeps looking back at the lady. And when he writes the wrong one, she goes like this, and he changes it back to an F. Remember that? That's actually back propagation.
yes. I like that example. That's a good example. Yeah, that's exactly it. Let's talk about how we turn that into code. Now, there's a lot here. We're going to talk about it. But basically, what we want to do is we want to find the loss, and then we want to minimize the loss. So that's where I was talking about how derivatives come into play, because a lot of times, basically, if you find the derivative and you can set it equal to 0, or you can find the second derivative and see if it's positive or negative, we can essentially find that point that minimizes the loss overall. And gradient descent is a big piece of this, which, Buck, I think you talked a little bit about in our last episode.
Yeah, I did. It's like a roller coaster, right? We come over the top and you're in a flat thing and you're going over a hill. And as you're still going down, you haven't minimized the loss yet. You're still losing, you're still losing, you're still losing. Then when you hit the bottom and there's no longer a number that's up or down, you're at the bottom. That's the loss.
Exactly.
You want to get to that gradient descent.
Exactly. And gradient descent is going to help us get there. And we talked a little bit about things like learning rates, how big we're taking these steps, how we get smaller as we get closer to the minimum. Now, part of this finding the derivatives, the second derivatives, it involves the chain rule. Now, a chain rule sounds very complicated, but the chain rule is just a way to take a derivative of something that has, multiple, let's say, x values, and sometimes it's inside square brackets, sometimes it's being squared, sometimes there's lots of stuff going on, but the chain rule is a way to break down and take the derivatives of things. Now, we're not going to teach the chain rule today, because that's something you probably spent a month learning in your calculus classes. But let's take a look at what that code looks like. So again, I'm just duplicating this code. We've got our initialization, so that's the same exact thing. We have the feed forward that we talked about, and now we have the back propagation. So what we're doing is we're going to apply the chain rule to find the derivative of the loss function with respect to the weight. So we want to know, how should we update the weights so that we can get closer to minimizing loss? So that's kind of what we're doing in this math here. Now, I'm not going to go through it exactly, but what you can see is we're basically going to be using the dot product. So basically multiplying the layer 1 values that come out of the feed forward with some of the sigmoid derivative. And then we're going to do that again. So you'll see the exact same code here, except we're going to be doing it with the layer before. But you see how we're going backwards. So we're going layer 1 first, and then the input layer first. And what these values show us is how we should change the weights. So that's why you see D weights 2 and D weights 1. And then whatever these values are, that's how we're going to add them to the existing weights, which is going to update our weight. So that's how we go back to the beginning. And then we're basically going to go feed forward, and we're going to, use our mx plus b, in this case b is 0. And then we're going to go back prop. We're going to minimize the loss and figure out how to update the weights. We're going to go back and forth and back and forth. And that's how we're going to basically train our model.
Awesome. So this is a very manual way of doing it, but it works, and it's really nice because you can actually see what you're doing there.
Yeah, exactly. And I think it's a good way to kind of look at learning how this thing works. Obviously, you don't want to do this every single time, but for learning.
Right.
Awesome. Okay, so now we want to take a look at an example. This is a very famous example to understand how to classify handwritten digits. But just for simplicity, we made this simple example, and we have 5 images, and the goal is to identify which image contains an L or not an L. So for example, this is an L, this is an L, not an L, not an L, this is an L. So this is a very simple example, but hopefully it helps. Now, in order to make numbers out of these images, what we're going to do is we're just going to make it a grid. And then we're going to roll this out. So you see each image is going to have 9 numbers associated with it. And this would be a 0, 1, 0, 0, 1, 1, 0, 0, 0. So basically 1 if it's lit up and 0 otherwise. So from that, you can see over here on the right side, what we're able to do is turn each of these images, we're going to roll them out and basically turn the images into a series of numbers.
Right.
Now, this is very common for any image thing that you're going to see. We're going to first turn an image into numbers.
And this is just a tensor.
Exactly. This is our tensor. So now what we have here is we can see we have our data set in the form of a tensor, and we're also able to see things like all of the data, including the label. Here's the features. So this is the tensor we're going to use. And then here are the labels that we'll use to help in training our model. Okay, so now what we're going to do is we're actually going to use that neural network we created. So I'm just going to create the neural network, just initiate it. And then it's very simple code because we're just going to, for I in range 1500, so this means 1500 times, we're just going to do feed forward and back prop, feed forward, back prop 1500 times, and then we're going to kind of print our results. So we can see it's trained very fast, and we're basically getting a confidence level for each item, whether or not this neural network thinks it's an L or not. And so you can see it's pretty sure that image 0 and 1, you know, we always start at 0 when we talk about coding, but images 0 and 1 are an L according to our model. Images 2 and 3 are not, and image 4 is an L. So if we go back to our images, we can see that in fact, image 0 and 1 are L's, and image 4 is an L, and image 2 and 3 are not.
Very nice.
Yeah, so this is a great simple example of walking through this. I encourage people to walk through this their own. Even try this sigmoid derivative just one time, because I think it'll help you understand what's actually happening here.
Okay, perfect. Perfect. Well, that's a good explanation. And again, there's a question there. What's a tensor, though? A tensor is just a block of numbers. No more complicated than that. Scroll up a little bit for us, Anna, and take a look at that block there, right there. That's a tensor. That's it. Just a bunch of numbers. So it's not complicated. And the way we got that, scroll up a little bit more, is we took the pictures of the L's. We made a grid out of them like that, and we unrolled the grid. We just took the first one and set on row 1, which is the first 3 blocks. The second block is colored. The second 3 blocks, the first one's not colored, and the next 2 are. And the third set of blocks, nothing's colored. 0, 1, 0, 1, 0, 0, 0, 1, 1, right? So it's very simple. Yep. That's a tensor. No more difficult or complicated than that. Now, they can be n-dimensional, so it can get a little weirder, but it's just numbers.
Oh, yeah.
Yeah.
Yeah, so I think that kind of leads nicely into the next thing that I want to say is like, hey, we saw this, and we'll take a look at how it gets easier with some libraries and frameworks, but that is certainly not all. I wanted to show this. This is a very famous kind of network. It's called the VGG16, and now every few years they have a big competition over who can get the highest performing model or neural network on the ImageNet data set. So it's a data set of a bunch of different images. Now, this is something that won a few years ago because it had like a 93% accuracy, which is very high.
Wow.
With 14 million images and over 1,000 different labels. So you can see these data sets get very large, and you're going to have to be able to have a lot of compute power. For example, to train this model, it took weeks using NVIDIA software. So it definitely gets complicated. But what I wanted to share here, what you're seeing is you might notice like initially it looks like the image or like the numbers we're feeding in are the same size as the image, but we can also do some different things. So we don't have to use all of the numbers in every single layer. Sometimes you use convolutional neural networks. So for example, you might have some filter that you apply. Maybe you can see this filter going through. So instead of using this as your input into the layer, you would actually use this. So you can apply these different techniques to use different filters, and it gets really complicated really quickly. And that's just one of these layers, right? Then you can do other things like here they're using ReLU instead of sigmoid, but it's the same thing from an activation perspective. So there's a lot here. So I wanted to also show some ways you can get hands-on. Now, probably most of the people watching the show have heard me talk about Microsoft Learn before. It's a great resource. This one specifically, I really liked. If you go into it and you look for PyTorch, it's 10 modules, 10 units on step-by-step. So like what we did, but step-by-step using
Very
PyTorch.
cool.
And you get a free sandbox. So you can see I have this free sandbox. I already activated it. And then you have the notebooks just built into the page. You don't have to spend the 4 hours to make sure you have all the dependencies for TensorFlow or PyTorch.
So it's just a notebook ready to go.
Yeah, notebook ready to go. And you can see they're going to be using different things from PyTorch. And you can see there are even different libraries specific to what you're trying to do. Text, vision, audio, they're going to have that. This one is related to the fashion IMNIS data set, which has a bunch of different things. But you can see how they're making it a little bit easier than some of the things we were doing, how you're just going to define the sequence of layers you want applied or the stack. And then you can just kind of call that instead of having to define each one and do the math. You can, in your feed forward definition, you can just call whatever it is you want to do.
Okay. Excellent. And by the way, for those of you on the line there, MNIST is Modified National Institute of Standards and Technology. So the NIST is the data set, and most often they've been converted to black and white and put in a grid. And those grids, a number that you will learn fairly quickly is those little 3x3 grids and a lot larger as well.
Yeah, it would be a lot bigger, a lot more numbers. I think what is like almost 1,000 numbers for a standard digit, because you have the 3 layers. It might be more than that. 3 layers of different colors, and then you roll it all out into a number, and it's a very much longer than 9, like we saw in our example. But just to continue, we talked about the feed forward. Now it gets a lot easier because you can just use this lost out backwards, and you can also add some optimization. So PyTorch is going to make it a lot easier, and you can run your different epochs, and then you can load your models. And what you could do here, which they're not doing exactly in this module, but they have a few where they do, is you can actually then export this model or translate this model into an Onyx model that you could then deploy in SQL, which is pretty cool.
Wow, that's impressive. Very cool. And you learn the whole way. This is very cool. I didn't know about this resource. I'm glad you shared that.
Yeah, it's really cool. And so this was PyTorch. And just for completeness, I wanted to mention how you can do the same thing with TensorFlow and Keras. Keras also makes it really easy because you can see here, you can just add your layers if you want a dense layer, what you want the activation to be. You can even name your layers. So there's really a lot of stuff. Let me see. I think you can also do convolutional networks and filters in here. Yeah, so you can see a convolutional 2D. You can see how you're going to filter it, what strides you want to take, and your activation. So really, these libraries and frameworks are making it so much easier, but it's important for you.
A lot easier, yeah.
Yeah, exactly. So lots of things for you to go play with. And speaking of that, I also wanted to mention this Cloud Skills Challenge that we have going on. So I don't know if you've heard of this, Buck, but it's called 30 Days to Learn It. And what it is it's a skills challenge that you can basically register for. And if you complete all the steps in it, they're going to give you like 50% off to actually go get certified. So not only did you go through the content, but now Microsoft has said, check, yep, you went through it, you passed. Now you can go, maybe even get a new job or something like that.
Very cool.
Yeah, very cool. And if I were going to recommend for someone who wanted to learn more about this, you see there's a lot of different things you can do, but the Azure AI Fundamentals one is very good. I've gone through it myself, as well as the Azure Data Scientist one, which has a lot of the stuff you just saw today. Azure Synapse Analytics one is going to be cool because it's going to kind of integrate the data side with the machine learning and analytics side.
Fantastic. Well, thanks for sharing that too. I'll have to spread that far and wide. I've got a few friends looking to change careers, and that'll be great for them.
Exactly. Yeah, we think it's going to be, hopefully this will be useful for people. Buck, as we kind of like close up and come up for air, like, what do you think people should really remember from this session? What are some of the important highlights?
I think the important highlights to realize are that more data in deep learning is better, where it's not always the case for machine learning. So you just almost can't have too much data. Secondly, it can do a lot more than you might imagine. So if you can come up with a problem, there's probably a solution for that. And the third thing is to really understand the different libraries. And I would, you pointed out Keras, and I would actually recommend you start there. Keras is sort of the layer above even PyTorch and TensorFlow, wrapping those up and making it even simpler. So if you can find a couple courses on Keras, and we have the links there in the site, definitely just start there. That would be my recommendation, is to start with Keras.
Yeah, I think that's a great recommendation, and there's so many resources out there, and we put a ton in our show notes as well. I think our show notes points to our GitHub page. Again, that's aka.ms/SOSN. And you kind of gave us a teaser at the beginning, but I can't even remember. So what are we doing next time on something called Something New?
Yeah, ending on a rather ominous note. The next time we're going to talk a little bit more about responsible artificial intelligence. Microsoft is one of the companies. A couple of years ago, there was it was a head rush to get a bunch of artificial intelligence stuff done. And there were some misuses of this technology. And we're in a brave new world here. There was a recent news article, which we'll talk about a little bit more, where for the first time, a drone, recently, not an American drone, but a different drone, went on its own and identified and struck a target. This is a brave new world. Which, in other words, no human said, yeah, go ahead and attack that. All drones normally are used with human supervision. In this case, the drone was said, here's some artificial intelligence, figure out the right targets and go after them. And it did. And it was the first time in history that's happened. There are some things we need to think about. With great power comes great responsibility. So in our next episode, we're going to back up a little bit, and we're going to talk a little bit more about responsible AI.
Awesome. I think that's going to be a really good topic, a really important topic, especially because, like you said, over the past few episodes, we kind of given you some ways to learn, ways to get some more power in this space, but you have to remember some of the responsibility that comes along with this. And I'm sure we'll be talking a lot about bias too, because that's a big part of this space.
Yes.
Awesome.
Absolutely.
Cool. Well, thanks so much, Buck, for coming on our show today. Thanks for our viewers for joining us and being so engaging. We got a lot of questions, comments. I think we were able to address most of them. If not, you're free to add a comment now, and we'll try to get to it. Let's see. We got a few thank yous. You're welcome. It is our pleasure, mostly Buck's pleasure, to bring those shirts on screen and let people see them besides his mom. I'm just kidding.
Yeah. Hi, Mom. Yeah, she didn't watch this. She watched one time, and what her response to, I said, I've got this cool show. I'm super smart. There's all this cool thing. It's international. She said, that's a very nice young lady you have there working on that show. And I'm like, oh, okay. Thanks, Mom.
Well, hello, Buck's mom. I'm happy to be here as well. Awesome. Well, again, thanks so much for joining us. Next week, we have an exciting news update. We're actually going to be on Thursday instead of Wednesday next week. So update your calendar invites if you're using those. Hopefully you are, because we'll be on next week. And with that, I will pass it to our
let's
producer,
let Marisa take us out. Marisa, are you around?
I'm here. Thanks all. So special thanks this week to Wolfgang Pauli, Jeremy Reynolds, iSight, Learn TV, Channel 9, and as always, this show is produced by myself, Marisa Brazili, and Anna Hoffman. See you next week.